Hi folks, Mr. Ackerman here. Thanks for watching. Topic of today's video is horizontal motion and friction. We're going to start to take a look at how and why things move in a lot more detail than what we've already looked at. So far we've really talked about how gravity affects the motion of objects, especially when we talked about acceleration due to gravity. But for a more complete understanding of how and why things move, there's a really important force we have to talk about, and that force is friction. So that's the main idea in today's lesson. In a moment I'm going to ask you to pause the video, have a look at the questions that we'll address, as well as where we are in the homework schedule, and also what the learning goals and success criteria are. So please do that right now, and then come back. All right, and you're back, and we're going to dive right into this. So here we go. First screen, I'd like to give you a little bit of a very, very brief, actually, history lesson about famous ideas relating to how and why things move. If we go way, way back to the Greek philosopher Aristotle, maybe you've heard his name, well, he's famous for a lot of things, but one of them is trying to figure out what are the rules of motion. If you think about it, understanding the universe involves understanding how and why things move. Well, Aristotle thought, and you can certainly understand why he would think this, he thought that forces were required to maintain motion, and he thought that objects tried to seek their natural state of motion, which was to be at rest. Now, to try to understand what this really means, I'd like you to look around you. You're probably in a room, maybe studying physics right now. Look around you. What do you notice about all the objects and their state of motion? Well, most of them are not moving. Of course, you might be listening to this in the car on the way to or from school, or maybe you're on the bus. Of course, now things are moving, but within the bus or within the car, look at the driver next to you, the steering wheel, maybe a can of Coke in the cup holder. Those things are not moving. It's fair to say that unless you push on things, they tend to be at rest. Well, Aristotle looked around himself at the universe, and this is what he thought as well. Of course, he thought many other things. This is a very basic idea of what he thought. Is that correct? Is it true that objects seek their natural state of motion to be at rest, and that forces are required to maintain motion? Well, many years later, probably something like 1500 or more years later, along came someone named Galileo, and you may have heard of him. He's famous for many things, among them also ideas about understanding motion. And his thought was actually quite different from Aristotle's. He thought that the only reason a force is needed to maintain motion is if another force is counteracting that object. So unlike Aristotle, who looks at an object that's sitting on a table and says, that object wants to be at rest. And if I push it to get it moving, obviously a force is required to move it, and if I stop pushing it, it comes to rest. Unlike that, Galileo says, no, that's actually not the case. Galileo thinks that if there were no forces counteracting the motion, then a pushed object would keep on going forever and ever, which is really strange because we just don't see this on a daily basis. So to understand what he's talking about, let me show you what I mean. We're going to go to the PhET website again, and this time the simulation under the physics unit under motion is called PhET, Forces in Motion Basics. So let's have a look at that. Here it is. There's 4 tabs across the top. You're going to click on friction. You're going to hit reset all in case everything's not reset. You're going to see this robot guy and a whole bunch of objects at the bottom. So what you can do is take, click and drag on, let's say, this crate here. And now you have a choice of applying a force to the right or to the left, a certain number of newtons. You can either type in the number of newtons or you can click and drag this slider. Now, up here, you can check some boxes. Do we want to see the direction of the force as a vector? Yes. Do I want to see the value of the force? Sure. I'd also like to see the speed because this is how we measure motion in many instances. And friction, let's start off with a little bit of friction, somewhere in between none and a lot of friction. So here we go. We're going to push this object to the right. I'm going to push it for a certain amount of time. Before I push it, I want you to pause the video and predict what will happen to the speed as I'm pushing and what will happen to the speed once I stop pushing. So pause the video and think about that and then come back. Okay, you're back and here we go. Let's give a push. We're pushing this way and I'm holding the pushing, looks like 453 newtons. The object's speeding up and there is friction. Now I let go and the force goes to 0. But the friction force is still there. Friction is a force that opposes motion. It acts when objects slide past one another. We're all familiar with friction. You see the speed coming down, friction is gradually slowing us down, and once more we are at rest. So going back to this screen here, Aristotle explains this by saying a force is required to maintain motion. Is he correct? Yes, he is certainly correct that a force is required to maintain motion. He thinks objects have a natural state of motion that they prefer to be in this case at rest. And is he correct? Well, assuming objects really do have this natural state they want to be in, then it looks like he is correct. So let's give him a check mark. Good job, Aristotle. But now let's look at what Galileo's saying. He's saying the only reason you needed that force to maintain motion was because another force was counteracting the pushing. You and I know that this force is called friction. Galileo says if that friction force were gone, the object really would keep on moving without the aid of any more forces. So let's see if he's right according to the simulation. Let's get rid of friction. Slide friction all the way to the left, and you see suddenly the ground freezes. There's an icy surface. Icy surfaces often have very little friction. So let's reset everything actually. Friction down to 0. Show me the value of the forces and the speed. Ready? Get the block up there and give this a push. Here we go, and hold it right around the same value I had before. This time no friction counteracting the pushing. Speed is going up, and I let go. The forces go to 0, but what do you notice? The speed stays where it was before. In other words, the crate really does keep on moving forever and ever because there are no forces counteracting it. Now, you may argue this is just a simulation. Is this really what happens in real life? Well, try to imagine the last time that you were maybe on skates on ice. Maybe your skates were recently sharpened so they were really able to let you glide and glide and glide. You gave yourself a push at one end of the ice and you wanted to see how far you could go on one push. Well, if you've ever done this, you actually go quite far if the ice is very smooth. Maybe the machine that smooths it out, the Zamboni, has just gone over it. Maybe your skates are really sharp and you gave a nice push. You might make it quite far across the ice rink. Same thing happens when you're driving and you skid on ice. This is a time when drivers all wish that they could apply the brakes and slow down, yet to their chagrin, they end up gliding often into another car or possibly into the ditch. So just ask any driver about the forces needed to maintain motion when you're on ice. There's actually little or no force needed. You'll just keep going. So let's go back here and see whether Galileo is right. Are forces only needed to maintain motion if another force is counteracting the motion? Yes. Will objects keep moving without the aid of any forces? Yes. So it looks like they're both winning. However, we got to go back to Aristotle and see that now forces are required to maintain motion is actually wrong. It only looks that way if there is friction acting. Do objects seek their natural state of motion, which is at rest? No. So actually it's Galileo who is correct, and sorry Aristotle, you had some ideas right, but only because you were kind of tricked by friction. All right, so going back to this is a really fun simulation that you can use. Watch what happens, by the way, if I increase friction suddenly. Now the friction force is doing what to the speed? It's slowing it down. And the more friction there is, the more rapidly the speed goes to 0. Eventually we come back to rest, which you're going to see right about now. All right, fun simulation, download it. It's free, doesn't take up much space, and it won't download any viruses to your computer. And you can use it to help learn about physics. All right, moving on. So what are the different kinds of friction and what is friction? Well, we've already seen that friction is a force that opposes motion. Because it's a force, it is of course a vector, so it's got direction and it's measured in newtons, as all forces are. But did you know there's different kinds of friction? What are the different kinds of friction? Let's have a look. This picture over here, I'm sure we can all relate to this, pushing an object like a piece of furniture across the floor. In this situation, the guy is exerting a force forward. We might call this an applied force. And if you go and do this with any object, whether it's a textbook being pushed across the tabletop, or a desk being pushed across the floor or whatever, you know that there is a force that opposes this motion, and we call that force friction. So I can write in F, like that. Of course, there's also the upward normal force, and there is the downward force of gravity. However, as long as we're staying on level ground, the gravity force and the normal force are often equal, which means really this is a fight between the applied force and friction. Well, think about what's happening here. The object is sliding across the floor, and therefore we call this a sort of sliding friction. And I've written that up here. I see I forgot a little bracket sign. I've written that here as sliding friction, but in physics language, we call that kinetic friction. So you'll see FF with a little subscript K for kinetic. All right? But there's something else that happens. What I want you to do, if you can, pause the video and go walk around your house, or maybe whatever room you're in, and find a heavy piece of furniture that's been sitting in the same place for a long time. Maybe it's the kitchen table or a fridge or something. Give it a light push, and what you're going to find is if you push lightly, it doesn't move. Push a little bit harder, it still doesn't move. You have to push quite hard to get it moving. Even though you're pushing and there's no motion, this is a strange kind of friction. We call this sticking friction or static friction. So when you can push, but there's no motion, that one is FFS for static. And it's very interesting, but if you've ever given an object like a fridge a big push and then finally got it to move, what you may have found was that it was hard to get the object moving, but it was easier to keep it moving once it was already moving. This gives us an idea that static friction is often a little bit more, a little bit greater than the sliding or kinetic friction force. So it's often true, not always, but often true, that static friction forces are a little bit greater than kinetic friction forces. You might be able to see this if you go push something across the floor in your house. Another kind of friction that's very interesting to study is what we call fluid friction, also known as drag. And this picture down here with the jet fighter gives you an idea of what that friction force is all about. You've all seen pictures of an airplane flying through the air. You've seen a skier trying to go downhill as fast as possible. You've seen swimmers going as fast as they can through the air. One thing they all have in common is they like to streamline their bodies. The skier and the swimmer streamline their bodies. The aerospace engineer who designs this airplane gives it really smooth curves, really pointy shape like that, so that it cuts through the air better. This cuts down on what are called drag forces. This is a special kind of friction called drag or air resistance, FD, it's often written as. It's a very complex branch of physics to study drag forces, and if you're interested, you should start by maybe checking out the Wikipedia page on it, which is not bad. It'll get you a start on what are the formulas involved and what are the factors involved in predicting the amount of drag. However, we aren't really going to talk too much about fluid friction. We're going to talk about these two over here, sliding and sticking, or kinetic and static friction. So let's see how we're going to do that. A lab that we're going to do in class is demonstrated by this diagram here, which by the way is in your textbook, the book being Physics 11 by by Addison Wesley. And what you see here is a block of wood with a weight or a few weights on top of it, a couple of hooks, and one of those Newton spring scales. What we're going to do in class is we're going to pull a block like this across the tabletop, or maybe across a piece of wood or a piece of plastic or something like that. We're going to see how many newtons of force need to be applied in order to get the object to move at a constant velocity. Because if we get it moving at a constant velocity, then it'll be safe to say that the amount of pulling that we're doing this way is getting balanced by the amount of friction acting against the block. All right, so I'll repeat that. If we can pull at a steady, slow rate, then the amount of friction and the amount of applied force will be the same. So what we do is we try to load a bunch of different weights on top of the block to make it heavier and heavier, and we see what are the different applied or friction forces that are required to get the block moving. Now, let's draw the free body diagram here while we're at it. There's an applied force that I just discussed. There's a friction force that I just discussed. And there's also, of course, gravity. And there is a normal force. Now, these two are equal, as I discussed, if we pull at a constant, steady speed. And of course, normal and gravity are equal if we've got a situation where the object is not accelerating up or downward. So, what we can actually plot is our pulling forces as a function of how heavy this is. Now, how heavy this block is related to Fg, that's equal to mg, but it's also related to Fn. So we could actually plot either the normal force or gravity on the horizontal axis. Now, why do we do the normal force? I'll explain that to you a little bit later, but for now, since the normal and gravity are the same, I'll write that in there. But allow me to just put it as Fn. Here's what we're going to find. I'll give you a little hint. We are going to find that there is a straight line relationship, which, just like we've seen in math class, y equals mx, where m is the slope, well, here we're going to have F friction, down here, equals slope times Fn, where the Fn is equal to Fg. Now, the slope here is obviously constant. We have a straight line. And in physics, since this straight line is very important to the study of friction, we give it its own Greek letter, the Greek letter mu, which is the symbol, it's like a fancy U, like this, with a little tail on it. So what you're going to see written is Ff equals mu times Fn. And that Greek letter mu is called the coefficient of friction. Coefficient being a number like you learned in math class. Ff equals mu Fn is the formula for calculating the friction force based on the normal force acting on an object and some constant. This, by the way, is the fact of the day. Make sure you memorize this formula. It's not that I'm not going to give it to you on a quiz, but I want you to memorize it because people often forget how to calculate friction even when they see this on the formula sheet. So today this is the fact of the video, just to memorize that formula. But getting back to things, where do you get this number from? Well, you get it from doing a lab where you pull objects across a surface. You try many different objects, and what you find is that the mu value changes depending on what objects are in contact. Like if it's a wooden board in contact with a wooden block, you get some value of mu because the friction forces and the normal forces give you a certain slant on that graph. On the other hand, if you did a brick against a wooden board, you would get different forces, you'd have a different slope. What if you did rubber against ice, as in rubber tires on your car against an icy road? Well, Table 3.1 from the Physics 11 book by Addison Wesley gives you some combinations of materials that are in contact with one another and the coefficients of friction. But look what they do. They split it into the static values and the kinetic values. Because remember how we discussed, when you push an object, sometimes you need to give a little bit extra push to unstick it, to get it moving in the beginning. And that's why the static friction force is often a little bit more than the kinetic friction force. Well, that is reflected in the fact that sometimes the mu values are a little bit higher. If you look at these, the static friction values are a little bit higher than the kinetic friction values, although they're not always that much higher. Sometimes, like down here, they're the same. It just depends on the particular situation. Another thing you notice, How about, let's take a look. Rubber tires on dry asphalt. What do you notice? The mu values are around 1. But rubber tire on ice, suddenly the mu value drops very low. There's very low friction for rubber tires on ice, and that's why if you go driving too fast and you hit an icy patch and you hit the brakes, you're not going to be able to stop. You're going to go sliding. You're going to go sliding in a straight line. You're going to try to turn the steering wheel to avoid hitting something, but that won't make a difference because there's very little friction. In other words, you'll be doing this kind of motion here that we talked about earlier. You will not be doing this kind of motion where your car comes to rest because it wants to be at rest. All right, so let's now have a look at how we actually use these, this equation and these values in a problem, and then we'll wrap up. So here's a question also out of the same book. An 80-kilogram skier is using waxed hickory skis on wet snow. Calculate the force of friction on the skis as the skier glides along the level. They mean on a horizontal surface. So I'm going to draw this. There's a skier who looks like this. Skier is wearing skis, I hope. Has ski poles, maybe has a nice scarf there and a toque. There we go. Okay, so here goes our skier. And we know a few things. We know the mass is 80 kilograms. And we know that for hickory skis on wet snow, if we look in this table here, what do we find? Waxed hickory skis on wet snow, the coefficient for static friction is 0.2, but for kinetic friction it's 0.14. So let's go back here. It says the skier is gliding. So is this a kinetic situation or a static situation? I think you can guess that it means kinetic, so we're going to be using mu k, which if I remember correctly was 0.14. So we can write that in here. Now the skier is gliding. What are the forces acting on the skier? Let's draw the free body diagram. You know there's gravity, which is acting straight down. That's not a surprise. And in fact, we can calculate the force of gravity. That's mg. It'll be 80 times 9.8. And I'll get out my calculator in a minute for that. What else do we know? We know there's a normal force, which if you are on level surface, the normal force is equal in magnitude, so I'll put a little tick mark there, to the gravity force. Now, there's definitely friction. If you glide across even snow with freshly waxed skis, there's always going to be some friction. May not be a lot, but there will be some. You can't glide forever. Because it's gliding, we will put FFK. But is there a forward force? This is a question that we should answer. Is there something pushing the skier forward? Well, if the skier is actually pushing with his or her skis and or poles, then definitely there's applied force. However, have you ever skied and just glided along? Well, if you're gliding along, you'll know that you don't have to push, you can keep going. And as we think back to Galileo versus Aristotle, you don't need a force to keep you moving. And as we think about the simulation here, when there's very little friction, you also don't need a force. You can push, get something moving, and when you let go, it'll keep on moving at a steady rate. Or if there's a little bit of friction, it'll slow down gradually. Well, that's what the skier is doing in our example here. So is there an applied force? None that they talk to us about, so we got to get that out of our minds. That does not exist here. So what is the force of gravity? That's 80 times 9.8. I'm going to run that through my calculator right now. I get 80 times 9.8, going to be close to 800. I do get 784 newtons. And so right away I know that the normal force is also equal to 784 newtons because these are balanced vertically. And now I can start writing out the rest of my solution. What is the force of friction? Well, remember the fact of the video. Force of friction, in this case kinetic, will be equal to mu, but the kinetic value, times Fn, which is 0.14 times the 784 newtons. And so if I multiply these, what do I get? 109.76 sig figged to 110 newtons, which should be written as 1.1 times 10 to the 2 newtons. And that is how you do this kind of question. Just to wrap up, I did ask you to allow me to plot Fn instead of Fg when we looked at this graph here. And you may still be wondering, why is it Fn? Why didn't he just plot Fg? After all, they're the same. Well, here's what I want you to do. I want you to take your hands and rub them back and forth together. I'm going to do this too. I don't know if you can hear the sound. We do this in the winter because it keeps our hands warm. We create friction. Now, question for you. If you want to be warmer, what do? You can rub faster, or you can press your hands together harder. In other words, pressing together harder leads to more friction. Another question. What is the force that is pressing your hands together? Is it gravity? It isn't. Gravity is not what's doing it. It's your muscles that are pushing your hands together. Well, when your hands are in contact with one another, therefore, it doesn't help to talk about the gravity force. It helps to talk about the contact force between them, in this case caused by our muscles. That contact force is actually the normal force. So you've just seen by rubbing your hands together, it's not really gravity that leads to more or less friction. It's the contact force, the normal force. So even though those two are the same in this particular situation, and they're the same in this particular situation, so we often use gravity to figure out the normal, it's not always the case. And that's why the friction formula has Fn in it, not Fg. That'll start to make more sense as we move through the unit, but that is the end of the lesson. I hope you've enjoyed, I hope you've learned something, and I'll see you in class. Thanks for watching.